Chapter 2, Section 4. Chapter 2, Section 4 introduces the notion of the second derivative. As the name indicates, this is the derivative of the first derivative. It's a rate of change of a rate of change. This is sort of a hard concept to conceptualize, but the most common known second derivative is acceleration. Now, we start with position in physics. If you take the derivative of position, you get velocity. And if you take the derivative of velocity, you get acceleration. We'll go much more into depth with this in Chapter 3, but we need to do a brief overview of these second derivative things and how we can use them. First off, the notation of second derivatives is very similar to the notation of first derivative, so make sure you're careful about reading questions so you know which one you're working with. In first derivatives, we use the notation of either f prime of x or dy dx. With second derivatives, we have f double prime of x, notice that there's two apostrophes, or d squared y over dx squared. Now, we said the first derivative represents the rate of change of a function. The second derivative represents the rate of change of a rate of change. So when you're looking at questions to see if the second derivative, look for the double prime notation or the d squared y over dx squared. Remember from before, we had the three basic rules of first derivatives and how they were related to the original function f. We said that if f is increasing, then the first derivative will be positive. We said if f is decreasing, the first derivative is negative. And if f is constant, then the first derivative will be 0. The same rules can be applied to the first and second derivative by shifting everything by one derivative. What that means is if f prime is increasing on an interval, f double prime will be positive. If f prime is decreasing on an interval, f double prime will be negative. And if f prime is constant, then f double prime will be 0. Again, this will come up much more in Chapter 3. So, what does f double prime of x tell us about f of x? This is the million-dollar question. This is what you're going to be using now, and it's going to be the most important part of second derivatives. So usually we want to know information about the original function. So we want to know how f double prime affects f of x. The second derivative tells us the concavity of the original function. This is a great relationship related to something visual. So here, if the second derivative of a function is positive on an interval, then the original graph of f of x is concave up on that interval. And remember, concave up means it looks like a cup and that it will hold water. If the second derivative is negative on an interval, then the original graph is concave down on that interval. And again, concave down means it looks like a hill. And if the second derivative equals 0 on an interval, then f of x is neither concave up or concave down. When we get into a later chapter, we'll discuss exactly what this point is and how we use it. But for now, you just need to know that it's neither. So let's look at a graph. So if we have an original graph here, how can we talk about the places where the second derivative is positive and negative? Well, we can do that by looking at the concavity. So here, we want to find wherever it's concave down. So again, it's going to be concave down when it looks like a hill. So between x equals -1 and approximately x equals 4, you can see that the shape of the graph is concave down. Therefore, the second derivative is going to be negative on this interval, because again, second derivative negative equates to concave down. This works in both directions. So now we want to look at where it's concave up. It's going to be concave up wherever it looks like a cup or a U where it will hold water. So between x equals 4 and x equals 8, you can see that it has that upward shape. So there it's concave up, which means that between 4 and 8, that second derivative is positive on the interval. So this is something you'll be doing a lot in this section, looking at graphs and concavity so you can say where the second derivative is positive and negative. The other thing you may have to do is look at tables, so let's take a look at one. So here we have a table that has a row for x, f of x, f prime of x, and f double prime of x. So if we want to look at the concavity, we want to look at the sign of the number so we can figure out if it's concave up or concave down. So the graph will be concave up whenever the second derivative is positive. So here you can see that f double prime is going to take positive values when x is 0, 1, and 2. So for x between 0 and 2, we will be concave up because that's where the second derivative has positive numbers. Similarly, f of x will be concave down whenever we have a second derivative that's negative. So we look for the negative numbers, which is between 3 and 4. So we know that between 3 and 4, we will be concave down because the second derivative is negative. And when we get to 5, we'll see that we are at 0, so it's neither concave up or concave down. So again, you're just looking at the sign. The number itself for a second derivative is not too important to us. What we're looking for is whether it's positive or negative, so we can say something about the concavity. So now would be a good time to try the homework from Chapter 2, Section 4.